and you should start looking at the final project, at least forming the team and also some idea. Maybe I will dedicate next Tuesday's lecture into the subject of final project. The other thing I do want to tell you is that in case you haven't heard, the university has decided starting next Monday, all the classes will be going back to the university in person, which means to all of you is the following. I, as an instructor, if I tested negatively, which I will go test probably tomorrow, then we're going to do in-person lecture. However, some of us still, for whatever reason, still want to engage the class online, which is fine with me. So what I'm going to do is I'm going to do lecture in person, but at the same time, I'm going to turn on my Zoom with recording, also with share screen. So you can still participate using online, while some of us are online, some of us are will be on campus. It's your option. The only issue, I have done that last quarter, pretty much doing both Zoom and live lecture at the same time. The only concern I have is that if you have any question from remote, usually in the lecture hall, which is, I don't even pay attention to what's the chat message, I might forgot. So, so you might want to wait a little bit patient. And then students who are in person might want to remind me from time to time to look at some of the issue from the online, from the online Zoom. Okay, that's the administrative issue. I would like to tell you that. Okay, now let's go to the. Oh, I should do this. Let me go to my PowerPoint. Yes, my PowerPoint is here. Okay, now I can share. Before I do that, is there any? That's a good question, Angela, regarding the office hour. By default, my office hour is going to be in person, but we might, I mean, maybe, you know, initially, let's still do office hour online. That might be easier, okay? Okay, can you see my screen? Everything okay? All right, good. Just double check. Yeah, okay, thank you. Okay, we're going to talk about distributed file system, or in general, distributed system. We're going to touch on a variety of topics related to distributed system. Particularly, we'll be looking at distributed file system. Here is a plan I might pursue, but I might change it. This is just tentatively. I will try to get through NFS and AFS very soon. And I like to focus a lot on GFS, which is, when I talk about GFS, I'm not talking about only the GFS, but also I have to talk about a few distributed protocols such as two-phase commit, which is a element to support a system like a GFS. I don't think I'm going to, this morning I think about this, I probably don't have time to talk about CODA, which is something to support mobility, but I might address some of the issue that's related to the final project. Okay. All right, so what is a distributed system? So a distributed system is try to stitch more than one file system distributed on the internet and provide a integration figure as if all this separated file system looks to the application or to the client that is a single tree, file tree of hierarchy. So one of the unique tool for us to be able to present this capability is using the command called mount. So in this case, you can see that the file system is actually in ftp.cs.ucdavis.edu, which is a local file system. And I want to actually include a server, another file system, another tree from Yahoo. And therefore, I want to mount this server location. The name is server.yahoo.com, and on this one. So what I need to do is just, okay, first, before this happens, the remote file system has to export the portion of the directory it want to expose to the public through protocols such as NFS, Network File System. And if that's actually happened, then essentially you can use this command, the button. What you do is mount -t, the type, the protocol of the mounting is NFS. And then you take, this is the remote information, including both the URL and the directory name where the portion of file that's actually being exported. And then I'm actually mounted under my local file system of /usr. So essentially what I'm doing is I'm taking the whole thing and mount it under this directory. So that's conceptually this stitching is doing. So right after you connect this, and essentially you actually have a unified view about two file systems, but under the same file hierarchy. So it's kind of transparent, kind of convenient for you to be able to manipulate. Okay. And in distributed file system, there is a few issues we want to take care. Transparency, I already mentioned. Location independence, pretty much similar to that, is that, well, regardless where is your file, it looks as if it's locally to you. And they all have to deal with issues such as reliability and crash recovery, because if it's connected to the internet, you have no control. And therefore, maybe the internet was disconnected, and maybe the server on that remote location had a power outage, and such that it induced a crash. And then, of course, that in a distributed system, you have two scaling issues. One scaling issue is about the number of server or number of a client that you need to deal with. The other issue is that those clients, potentially a large number, will try to access the same file at the same time, or not even the same file, but the same location, try to take away some of the data that they are all interested to obtaining. And therefore, you might have a bottleneck. And depending on the situation, depending on the contention about those resources, and sometimes it will causing the response time for a distributed file system to degrade significantly because it's a hotspot with everybody. Okay, and then there is an issue of correctness and consistency. I should actually first talk about what do I mean by correctness of consistency. So there is a consistency criteria we call one copy Unix semantics. So what do I mean by one copy Unix semantics? Means that regardless how you build your distributed system. By the way, some of the distributed file system allow a single file has multiple copy at the same time. I mean, this is essentially pretty much like a soft update we're talking about. You essentially have one copy in the hard disk, one copy in the memory. So that's actually two copies. So what in a distributed file system, this phenomenon becomes so common that we have different versions of file exists in different places. So one copy Unix semantics basically say the update, the write operation to the file is going to be sequentialized among all the clients. So it means that when you modify a file, then any subsequent read to the file need to be able to see the newest change. That's called one copy Unix semantics. I mean, this is pretty strong in terms of you require essentially a sequential access to the right access to the file, so you can actually make sure that, for example, somebody actually update account information about how much money you have. Then you want that to be immediately visible to all other branches of the bank, and such that you won't be able to withdraw more money than you should, for example. So this, however, in a distributed file system, it introduced a lot of overhead to maintain this kind of this level of consistency. So typically, we're actually doing two different ways to address this, to kind of balance between consistency and the performance. So on one hand, in many of the distributed file systems, we actually adopt a weaker consistency criteria, which we will actually see that what kind of weaker consistency we're talking about. And that basically allow us to be able to not enforce ourselves to write immediately all the data back to the server and to block, in fact, all the subsequent access to the data until the update is done. So that is definitely, you saw that, we talk about that in soft update. It's actually addressed the same issue. And the other issue, which is getting into another topic called transaction. So, I mean, we try to sequentialize a bunch of operations such that they maintain certain kind of consistency. But on one hand, one copy Unix semantics is not strong enough to actually handle, especially when we consider a group of modification, need to modify the file that need to be consistently updated. So the good example is journaling. So journaling is all or nothing. So one copy Unix semantics only say when you modify this, everybody should see it. But the thing is that, as you familiar with the journaling concept, that we want the other application to actually see the every modifications plural in the whole group. And I don't want you to see partial or think. This is called the transaction concept, which we actually will talk about. How do we actually be able to enforce a even more strict Unix file semantics, and yet still be performance will still be acceptable. Okay, so that's just let you know this is the issue we're going to talk about, and it's actually quite challenging to design the distributed file system, and a lot of cases we have to really consider what's the property, what is the characteristics about the application that's going to use this distributed file system, and then that will help us to determine what should be the appropriate design for consistency, either transaction model or other kind of weaker type of Unix file semantics. Okay. Okay, so typically I'm going to introduce, starting to talk about the first two is NFS and AFS. So typically in this type of design, we split the program into the client side and the server side. So in a distributed system, on the right-hand side is the remote file system. That's actually, for example, server.yahoo.com, as I mentioned earlier. And you have your client which want to access the file. So what do we mean by client? So the client is doing, if you think about what the, at least the first implementation of the distributed file system, when we think about what client is doing, we really think about what client would have been doing if the file, the hard disk, is not in the remote, it's actually in local, in our local single processor file system. So essentially, naturally, we want to see, okay, we want to have a distributed system. We want to allow the application to do all kind of file operation, such as open the file, read the file, close the file, or access the directory information and look at the file status. And they can do everything as if the file is actually local, just like what you did in the whole set of lecture number 1. And yet this 2 green box is the distributed file system protocol to provide the gateway to allow those operations, instead of accessing the local machine, they will be communicated to the server on the right to actually accomplish what they want to do. So it's a seamless design such that the client doesn't need to modify his application at all, because everything will be done by those 2 green box. And for those of you who just finished homework assignment number 1, those 2 green box is HW1 client.h and HW1 server.h. Okay, is using exactly RPC to actually do this kind of transformation. So first, let's talk about NFS, which is introduced pretty early in the by Sun Microsystems, now part of the Oracle. It's based on, okay, here is the reason why they start using remote procedure call. So over here, we use RPC XDR. XDR is extended data representation. This was the terminology in 1985. Today, especially with your homework assignment number 1, so the RPC is what we call JSON RPC, and the XDR is essentially JSON. Okay, so the newer version of RPC is actually based on a more human readable representation instead of XDR, which actually people worry about how to actually encode a fairly complicated object. So you can actually do this kind of remote procedure call to handle very general case. Okay, so that's what NFS is doing, is develop this. Okay, just let you know the rationale behind they use RPC and XDR. And it's really about, at that time, object-oriented is getting popular. VNO architecture is actually being introduced. The operating system has been more structured. And the reason in that process, people realize that, okay, if we are going to moving from this direction to make our operating system kernel more structured, which they see the advantage that the program is actually being cleaner and easier to understand. So then they realize if the traditional distributed file system, when people think about this, they're using message passing. They're basically having the client send a request to the server as a message and asynchronously receive another content moving back. So at that time, people realize, okay, but most of the stuff we want to do, I mean, if you look at the picture we have in this, most of this are actually synchronous. Basically, I make a call, I wait for the result to come back. And therefore, at that time, realized that, okay, maybe using RPC is a great idea. Number 1, RPC is a lot more readable because you can actually see what function you call, what's the parameter. It's naturally linked to your existing program, which whatever doing the operation to the local. and the thing is that also you utilize this, then a lot of the networking code related to this message passing will now be hidden under the whatever the implementation of RPC, which so make things really easier for us to do. In fact, I'm going to show you some code. I call it mini NFS, and in which you can see that how simple the code is. We can already implement two of the operation that's actually provided by NFS. So there is a design about NFS that's saying that the server this is called NFS, we call stateless. The server does not maintain any state about the client, which we'll see that. In general, that's true. That's actually stateless, means that it's a fundamental design. NFS want to make sure the server remember nothing. In contrast, AFS is stateful. AFS, Andrew file system, they try to make the server remember certain information about the status of the client, and they want to accomplish some other result. So we'll actually see that, but I do want to give you a warning at this moment, is that NFS is not purely stateless, especially in the later versions of NFS for performance reason, that they actually doing things very similar to what AFS is doing, because they need to keep the state in order to achieve the kind of performance they like to achieve. Okay. Okay, I'm going to skip XDR because now we should just remember XDR is a way to represent the data, which we can easily use JSON to represent any data we like. Okay. And at that time, it's called RPC Gen. In your program is called JSON RPC scrub, and basically will generate this file for you to use. Okay, so now I'm going to talk about a little bit detail about the operation of NFS. So I'm saying that NFS is essentially doing remote procedure call between the client and the server, and therefore, we need to know what are those procedure calls, means what are those operations. So basically, because it's stateless, so every operation is independent. Okay, it's independent because the server doesn't know what you did before. That's the difference. You can think about, that's kind of interesting, is your local file system, is that stateless or stateful? You can actually think about that. Okay. So let's actually take a look at the operation. So this is the NFS version 2, all the operation that it needs to support. Okay, so for example, you have the read. So read means that you can actually read from, just like you do read for your local file system, you can read from the client, and this read request will actually go to the server. And you can write, you can actually provide a end link or a symbolic link, you can manipulate directory. This is pretty much everything you need to do in order to create a file. I just want to explain a little bit. NUA is just testing. Okay, NUA is doing nothing, but just try to test whether the server is still alive and whether the server is actually connecting to the client. That's the only purpose of a NUA. Get ATTR, set ATTR is just getting the attribute regarding the file. Okay, all right. So
what do you mean by V2 in this scenario?
Pardon?
Just at the top bullet point, it just mentions V2.
Version 2.
Okay.
NSF has a different version. I mean, let me actually show you this. I just checked, so I think I still have the page with me. Sorry, let me actually show you this. Okay, so I'm going to show you this screen. Okay, this is from Oracle on information about NFS version 2 and NFS version 3. Okay, so they have a table to see all the comparison between the operation, like a create, there's no change. Stay FS is actually being replaced, but it's actually doing the similar thing. Get attribute, no change, and link, most of them doesn't change. Lookup doesn't change, and read is actually changed a little bit from 32 KB to 64 KB in order to boost the performance. And pretty much some of other things, root being removed. I actually didn't even include root there. And write cache being removed, okay? And write has been updated to handle 64 KB. So you can see that those are the operation that being included in version 2 and changing in version 3. And then in version 3, they introduce a few new operation, allow some kind of security access, allow some kind of directory access. Now they can actually have more stuff. And then they actually, this is for consistency, they can actually do some kind of commit, which we'll talk about that later. Okay. By the way, just to let you know, I actually take a look at this. The NFS was declared in the RFC request for comment. It's an internet standard in 1989. That actually has a protocol. If you're familiar with IETF, Internet Engineering Task Force, is actually declare all the network protocol because NFS is a application layer protocol. So it has an internet standard. This one is the standardization that talk about all this model. You can see here, over here, there's a bunch of operation. All the operation that we have is actually included in the RFC, such as get attr, root, lookup, and everything is there. Okay, and of course there is also a standardization for remote procedure call around the same time. That's because they need to have standardization in order to support the operation over there. Okay, now let's go back to the slide. Okay, so I want to ask you a question. If you look at the list, let's just focus on the version 2, the list we have here. There are some file system call that you have been using, I believe, or at least a variety of those calls, but they were not here. Have you noticed that which call have not been included in this list? What kind of things you will do with a file with that operation, and that operation is not here?
Probably open and close.
Yes, exactly. They don't have open and close. That's interesting. Open and close, which is important, right? When you open the file, when you close. And so just to let you know, the NFS have this design called stateless. Now I kind of lure into the discussion about stateless. So stateless means that if you do something at this moment, and the next time you come back to do other things related to the same file, then essentially I shouldn't remember anything about what you did to this file earlier. That's called stateless. Means that on the server, I don't have to remember what you did earlier, which is kind of good in terms of simplify the design of the server, because now the server is just handle one request at a time. After I handle that request, I'm done. One RPC call, that's it. And I don't need to remember anything. So in other words, in that case, open and close is actually a stateful operation, because when you open the file, you need to remember this file is open. Until you close, that file is still open, right? So essentially what NFS is doing is that open and close will never be sent to the server instead, because what open will be doing is that you need to remember where is your pointer for your read-write access point. So the next read and next write will actually get it from there. So that's called offset. So essentially the offset of a file that's application is entitled to at that moment is going to be managed, remember, at the client side instead of at the server side. So just to let you know, so if you open the file, only the client side is going to remember what is the position of your offset. The server knows nothing about that. But when you actually read the file, you actually know what offset you're going to read. So essentially the read NFS call is going to provide the absolute offset about where I'm going to read from that file and how big. So essentially at that moment is going to be open, read, close, and then send the data back. So to just let you know that I'm glad that some of you already found out that open close is not included. Okay, the second level of detail I want to explain is about for each of the call, you're going to provide some input argument, which we will actually see the code that I sent you. I hope you download the code. If you are not available using like a Unix environment to run the code, that's fine. You can actually run it later. I'll show some demo is recorded. So you have some input argument, and then you have the return result. This is essentially the client need to provide this, and then the server is going to reply. So for example, in the read system call, remember I say read is because what? Because it is a stateless design. So you have to actually say what's the offset and how many bytes I'm going to read. So that's why this 2 parameter is actually critical. What is the offset? I'm going to start reading for how many bytes. So it's open, do this read at this offset and count, and then close, and then you get the result. In the result back, you actually got the data, and you got the status to say whether this read operation is successful or not. And then FATTR just represent what is the file. It's some of the attribute about this file that you can actually obtain through that call. Okay, so this is, you can imagine that this part is going to be the RPC parameter. I'm going to send it over there. And this part is going to be return result from the server after the read is done. Okay, the things I want to catch your eyes at this moment is this thing called FHandle. So essentially, you can imagine that, well, when I do this distribute the file system, I have to let the remote, the server know that which file I want to read. Remember, this is stateless. So I have to tell the remote side which file I want to read. I mean, for example, lookup. I want to look up for a particular file name, then I have to know the directory, which directory I'm trying to access. By the way, if you look at the character, this one is called FHandle. There is something called file handle. Usually in the abbreviation, we say FHandle. It's a very critical piece of information in the whole NFS design. And when you do lookup, it's actually a directory has a file handle too. So every single node in the hierarchy has a file handle, FHandle. So the NFS protocol does not mandate how you're going to decide what is the FHandle. It means that the format, how do you obtain, that's totally independent of the protocol, but you must have one. So what's the purpose of FHandle? So FHandle is a unique sequence of identifier for you to identify a particular file in the server side, on the server side. Okay, they decide not to use the pass. I mean, obviously, the other way for me to decide to use the uniquely identify the file is actually using the full pass, right? /usr/include for me to do that. And they decide not to do that, but instead they want to use FHandle and to uniquely identify a file. And there are a variety of reasons for them to make this choice. But one of the reasons is that because it's a stateless, and because I might want to access the same file for a period of time. And in this meantime, the directory might change. It means that I move this file from one particular directory to another directory and move the other file into this directory. So if I'm using the full path name to access a file, I might not be accessing the same file. But if I actually use FHandle as a unique identifier to a particular file, and therefore, regardless how you change your directory, change your file name, or change the location of the file, that I will still be able to access that file that I want to access, okay, uniquely. So this is called FHandle, which is very important. I would say that for all the operation I showed you earlier, they must have FHandle. In fact, I will say every single operation, they need to have a FHandle. Okay, they need to have a FHandle. I will explain to you why. Okay, so now I want to let you guess. This at least is the first generation of NFS server implementation. How do they get this number FHandle? How do they actually assign FHandle to any file that's client might be interested? How do they actually assign that? Anybody want to give a guess? By the way, I'll give you a hint. That number is actually from our earlier lecture. Means in the first set of the slide. Anybody want to give a guess? Let me see if anybody provide the answer in the chat. Yes, I know. Yeah, you guys are good. Yes, it's actually I know. So the first implementation of NFS FHandle is the I know number. Remember, every I know in the directory has an I know number. That's the number used as FHandle. Right now, I think some of the file system deviate from that because you might be dealing with a file system which doesn't have I know in some sense. But I know number, the I know identifier is actually the FHandle in all these cases. Okay. All right. Any question?
Yeah, Professor, I had a question.
Sure, go ahead.
So you mentioned that NFS is stateless on the server side.
Mm-hmm.
Then how is it storing this information about the directories and files? If a client creates a directory and if the server stores a directory, it essentially becomes stateful, right?
Okay, that is yes. If you consider that as a stateful, it is stateful. It is. You create any directory, you create any, it will be permanently result in the persistent file in the server side. So that is a permanent, is a stateful. But the real stateful definition that we're talking about here is that whether the server remember what you did before. So for example, you say somebody create a directory, right? But how does the server doesn't know. Server know this directory got created, but server doesn't even know which user actually, which client create this particular directory. So basically, the client, the server essentially try to keep minimal amount of information. That's probably a better way to say stateless. But stateless is really referred to the open-close relationship. Okay.
Okay. Thank you.
You're welcome. Any other question?
Yeah. What if two clients trying to write to the same file or just creating the same directory using the same network file system? So would there be a conflict? Okay.
So yes, there are two situations. If two clients try to create the same directory at the same time, one of them will fail because you cannot recreate a directory, right? So one of the, in fact, in my program, you will actually see that, that one of them will fail. But if two clients, they both refer to the same file, refer to exactly the same FHandle, then essentially their result will mix. So it means that you change something and I change something, and then the result is actually, you're going to see that the result file that we both modify are actually has both our input into that. So that is actually an issue. There are ways to address that. For example, you can possibly put a lock on that file. And the thing is, NFS version 4, they actually have some mechanism for you to actually detect that since the last time you read the file, because you read the file, you want to write it back, that it has been modified already. So that capability is supported by NFS version 4. So essentially that, yes, that will happen, and the file, the consistency of a file might not be really protected if you don't use other mechanism to actually protect a more sequential access to certain file.
I got it. Thanks. So to some extent, it's just like what is used in GitHub, right?
Yeah, similar to that.
Okay, thanks.
You're welcome. Well, by the way, the issue you talk about, that issue will happen in single processor file system as well. Because if you have a two application, that's actually accessing the same file, right? I mean, could be, you could have the mixing of those two as well. Okay. All right, any other question? All right, so I want to talk a little bit about the operation, then I can actually go over to show the demo. So essentially what happened is that, okay, I actually want to do this. I realized I never present this slide. And when we talk about the first, so I want to now let me transition to my another file. Okay, this is the slides, including the first set of the lecture notes. I probably should starting from here. Yeah, this is the place I want to start it. Okay, I'm actually going to talk a little bit about the concept of mounting. Okay, so a mounting is essentially I want to integrate a file system, which is typically a hard disk partition, into the rest of the file system. I said it's a mount, is a stitching. There's two file systems together. So in the first set of slides, we actually talk about this kind of mounting among all the local file system on the same system. But the same concept can be applied to mounting a remote NFS file system, as we mentioned earlier. And the way it works is this, is that when you actually mount in the client side, that you actually have a vNode. You have a vNode representing that through this vNode, I'm going to access to this whole hard disk in the remote through NFS protocol. But in the remote NFS server, there is a root to every single file that actually contained in that remote NFS server. So this is what we call the mounting point of the NFS. So the mounting point, when you mount this particular NFS partition, that this mounting point, in fact, has a file handle. So the mount command that I showed you earlier, when they actually mounting a remote file system into here, the starting point is the FHandle for the file system. So you actually will get that file handle in the mounting process to do that. After you've done that, then essentially you're going to use the command called lookup, which I will show you example. So what is the lookup? The lookup is essentially you give me a directory, and initially that directory could be the mounting point, which is the root. And from there, you actually has the direct, the directory entry, which has the inode number, which now we call FHandle, as well as the name of the file. So you say you want to find a particular file that's actually with this name. You want to read or you want to write, whatever you want to do. And the thing is that how do I actually be able to deliver to you the file handle? You have to use lookup. So lookup is a new operation that's actually allow us to traversal through the NFS server file hierarchy for us to actually check whether the file exists. And if it exists, then I need to get that file handle of that file, because without that file handle, I cannot even do anything to actually be able to do, for example, read and write and get ATTR. I have to get that FHandle. Okay, and slowly what you have is that, okay, once you have that, and then you have something looks like this. When you open the file on the client side, then you actually start to have the vnode to actually matching up all the file. But each of the vnode, remember there is a vnode pointer to inode, which now is a vnode pointer to file handle in this case.
Professor, I have a question.
Go ahead.
What if after we mount a remote directory, the inode, the file handle that we get has the same inode number as a local file?
Oh, it's okay. It actually understands different file system. It understands when we look at the file system, there is a file system identifier. So your local hard disk, this partition has an identifier. This remote NFS, there is a mounting point also has the its own identifier. I maybe want to show you this slide. I actually went through this slide very quickly, so that's why it didn't. Maybe I haven't explained. To answer your question, assuming the first one, the first mount is the mount for your local hard disk. And the second mount is actually for NFS. So you can see that I'm actually linking all the vnode that's actually for that particular file system, but all the file system specific information is actually go with the mounting point. So meaning that when I'm actually using the node specific information, such as inode or FHandle, I actually will not just using that information, I will actually also using the file system specification information to actually know whether this inode number need to be used in a local file system or remote file system. Because remember, vnode has this VOP. It actually will, depending on whether your underlayer file system is a UFS or is an NFS, it's going to execute totally different function. And you will use that node specific information differently as well. Okay, does that answer your question?
Yeah, Professor, but if we have just the file inode and nothing else, that wouldn't be sufficient to identify them from each other, right?
Well,
we need some other information as well.
What I'm saying is, when from the application point of view, for you to use the file, you must have a vnode, right? You need to have a vnode when you actually want to access the file. And when you have that vnode, then the vnode will know whether this file system under this vnode, particular vnode, is actually local or is a remote. So application doesn't know, but vnode will know. And then the vnode will actually, based on because it's a different type of file system when you do mount, you mount the -t NFS, then all the operation, the vnode operation, let me actually see if I have a vnode operation somewhere. I have, yeah, here. You see, you have all the vnode operation. And this vino operation is going to be per file system different. So if it's NFS, it's going to do NFS type of lookup. If it's a local file system, it's going to be local. So in this case, if you're doing NFS, you have to have a file handle. But if you're doing local file system, you don't need to do that. Yeah.
Thank you, Professor.
You're welcome. Yeah, I know it's kind of challenging concept for us to understand that. But on the other hand, the good thing is that the starting with a vNode, then a lot of this distributed file system is essentially built on top of the groundwork that some microsystem already developed. Okay, so I'm actually going back to the other set of slides. Okay, so I'm going to share with you how the basic operation about a client server in the distributed file system. Then I'm going to show you the demo. I call it mini NFS, which is a really simple implementation of NFS. Okay, so essentially what the client is doing is that it needs to access a file. It needs to do something we call lookup. So what is a lookup? Lookup, if you think about, I want to read a file. This file must be contained in the directory. And for me to actually, okay, I one step back. If I want to read a file, I need to have the file handle of the file I'm going to read. But I don't have it. I only have the path, the full path name. I don't have the file handle. So you have to use a lookup. So what lookup does is that the file must be contained in the directory. So within that directory, if the file say that file is called XYZ, you want to read it, and you must give me the file handle of that directory that's actually contained the file XYZ. So I need a file handle one level up. So essentially, if you're actually dealing with an NFS file system, which you have nothing, you just started, then you have started from the root. Remember, when you mount, I only got one file handle, which is the root. Then from root, I can traverse for every single element of the full path. Then eventually, one level by one level, that I will actually go down the directory. I need to, by the way, I need to get the file handle for each of the directory. And eventually, I can go to that directory contain the file XYZ. And then I use a lookup to actually get the file handle. And after that, I can actually read the file. You see here, I don't do open and close. I just read with offset and with the count about how many bytes I need to read. Okay, so that's the operation. That's why you see NFS is really a sequence of this kind of remote procedure call, such as lookup, such as read. Okay, so I'm going to unshare my screen. I'm going to do that. Okay. Now I'm going to share my full screen. Okay, I just create this file. It's called the tar file that I published through Canvas is ecs251 w2022 mininfs.tar.gz. It's actually I actually just be honest with you, I just done this morning. It's like an hour ago. I said, hey, why don't I just take my your homework assignment number 1 and then try to make a simple NFS remote procedure call example. So I only got time to implement 2 function, 2 of the whatever maybe 15 or 20 function, but you already can see how that will work. Okay, I'm going to show that to you. You can actually just open it, and while I'm doing it, you can do it together. So this is directory. This is the file you have. So the thing is that with JSON RPC, I actually have to specify, right? Remember, I have to specify the remote procedure call. And this one, now I'm calling, instead of call homework1.json, I'm calling mini-nfs.json. Okay, let's actually take a look. What is 251 nfs.json? It's essentially have two functions. The first function is called lookup. So I want to call a lookup, and I still using whatever the core object. That's why I still have owner VSID, host URL, class ID, and object ID. But now you see I have a two different thing. One is called file name, one is called FHandle. So I introduced two more arguments so I can actually do the lookup. So by the way, lookup needs two parameters. One is the file name lookup, one is FHandle. This FHandle is not the file name's FHandle, is actually the file handle for the directory I'm looking up. Okay, so this is called directory file handle, and that's the first directory called lookup. And the second function I create is called create. So create, if you see the NFS definition, is actually because I don't have open a file. I mean, if I have open, when I open, it's like open. But because I don't have open, I can have a create. It's also stateless. So create is just create and it's done. Okay, it's not like a create have closed. No, just create, it's done. Just create an empty file. So when I create, I also have a three parameter. One is called file name. One is called FHandle. Okay, the file handle here is also the directory. Under what directory of that FHandle you want to create this file name. And then you have SATTR that when you create a file, you have to set certain parameter. For example, in this case, I actually put something meaningful is 0644. This actually represents the SS mode of the file. So I can set the attribute such that when I create a file, I want to make sure the file is everybody can read, but only certain people can actually modify or yeah, 644. That's the okay, and the rest are pretty standard. So I actually create this two function. That's how we actually do this, right? And then of course you just type a make. All right, and I'm going to create two windows. Just do that. So I'm going to run HW1 server. Wait a minute. Okay, I'm run the server, and then I'm going to run HW1 client. Okay, and now we can see that it's actually connected to the server. Interesting, the server, oh, you know what? I forgot to turn off the server from the other window. Let me actually redo that again. Server. Okay, so now you can see that the server is actually getting one call for lookup, two call for lookup actually, three lookup. Wait a minute, I make a mistake. I think I know one mistake I made. Here, receiving lookup. Yeah, I said create. Why it's actually print out different thing? Interesting. Hold on 1 second. I want to search for another place. I want to look at shadow directory.cpp. Lookup and create. Yeah, here I know this is a mistake I made. This is a create function. So I should say create. Okay. Sorry about that. Let me run this again. Let's look at the code. Okay, I'm actually running this. And basically now is one lookup and then two create, another lookup, another create. So there's about 5 call I actually made from the client. So I want to actually just go through the call and see why we're getting this result. This is essentially mimicking a interaction between the NFS server and the client based on this 2 operation. One is lookup and one is create. So number one, I just want to tell you is that the first file handle for the mounting point, I set it to be 00080 as a string. Okay, just to let you know. So let's look at HW1 client.cpp, which is the code that's going to run this. So it's very similar to your program, but you can see that this is what I did. First, I actually mount the directory. And the directory mount with this 4 parameter, it's just a remote object, right? It's a shadow object. It's only have this 4 parameter. And then what I did is you can see that the first thing I actually look up. I try to see, okay, so this is 000, this A0 is the file handle for the remote, for the, for the server, the file handle for that directory that I'm going to do the lookup. And I want to look up a file called my first file. Okay, so let's actually just kill this program here. Let's see what happened. Because initially there's no such file there. If I actually do this, I'm just doing one thing at a time. Yeah, I don't need to change that. Let me just kill this side. So if I do this, it actually say file not found, because you try to look up a particular file name with my first file. And by the way, the file handle is actually correct, that you can actually do a lookup. But the thing is that the file is just not there, so it will fail. So let me actually do another changes here. Now I can get rid of this. So I'm actually going to stop here. You can see that now I'm actually including 2 more operations. I actually create the file, but this time the first create is with arrow, because the file handle is incorrect. It's supposed to be 0000, and I put a 1 here, and then the second one is going to fail, but the third one is actually going to successfully create a file. So let's actually try to do that. This one just in case. Okay, you can see that the first one is error not found, and the second arrow is basically the mounting point, because you provide the wrong file handle for that directory for the mounting point essentially. So therefore it cannot recognize that, so basically it will fail. But then the third one, because you provide the right one, that is actually going to be successful. If it's going to be successful, then the next operation is actually going to create. Then the next one, when you create, it should work. So that's why the fourth line is going to create. And then after you create, you look up, you should be able to see that. But then after you look up, then you try to create again. You want to create under the same directory with the same name, and this one will fail because they will detect, the server will detect this file already exists, and you try to create a new file. So let's actually try to do that again. Okay, you can see that now the create is successful. So now when you actually do the call, the NFS lookup, which for that file, which is the file name, my first file, then it will return the file handle for that file. Now this file handle is actually going to be important for the client side to actually continue to open that file, not open file, to read that file or do whatever with that file using this file handle. And I said, after you create a file, and then the last one, you try to create again for the same file, the error will say, sorry, the file already exists, and it will fail to do that. So that's a very mini NFS operation. But it's actually authentic in the sense that it's actually using RPC to connect a client and the server. And of course, there's a lot of work can go into that to actually really explore into directory. I mean, the only thing I did is I created a, if you look at the code, I only create one single object, one single file called directory .h and directory.cbp, and then I create shadow directory and shadow directory.h, which is exactly the way I create for your homework assignment number 1. And let me just take a look at directory.h first. So inside directory H, I only have a 2 class defined. One class is called Duran, which is the directory entry. It basically includes only 2 pieces of information: the name of the file and the file handle. So this are just like a name and the inode number. This 2, and it has a default constructor for initializing those 2 parameters. And then this is the directory where mainly used. You can see we have 2 virtual functions. One is lookup, one is create. They're both associated with the directory. And we have the parameter, have the name, have the FHandle, and also have a vector of directory entry, which is containing all the file that within that directory. And then I have, of course, constructor for me to handle things. So it's very simple, but it actually can as a basis for us to grow a more complicated file system. Okay, any question? That's my quick demo. Any question? Okay, I hope you spend some time to play around the code and to try something to kind of learn a little bit about the distributed file system. Okay, I'm going back to my slide. I have about 10 minutes. Okay, so now you have some idea about what NFS is doing and how they're working. And essentially, this is the diagram about how you can potentially running NFS either in the kernel mode or in the user mode. You can see that here I have an NFS server, which is hooked under the VFS virtual file system. And here is my NFS client, which is under the vnode. That's why vnode is actually on top of that. And then you can actually issue remote operation doing remote procedure call to the kernel, or you can actually do you can implement NFS client as a user base. And then from the user base, you can actually also to talk NFS. By the way, I should let you know, NFS is a protocol. It's an application layer protocol. And therefore, when you specify, remember I showed you this RFC, which is talk about how do you specify the NFS protocol about what are the data field you need to put in. And so that data will be sending out through the connection TCP to the NFS server, and then you communicate with that. And that protocol is actually based on RPC. The difference between RPC and JSON RPC is that RPC is using XDR, which is a more compact representation of the data, but it's much less readable than JSON. While JSON RPC is essentially doing RPC, exactly the protocol, but the data they transfer between the client and server is based on JSON, and such that it's very readable and it's very easy for us to process, because JSON has been a kind of like a default standard for all kind of information technology services. Okay. So is there a question? Charlie and which you talk about NFS, or you talk about which part you would like to read? Yeah, I mean, there is a lots of paper you can read about NFS. It's a lot, and I can probably introduce 1 or 2 articles to do that if you're asking about NFS. Okay, I will. Thank you. I will provide that. Okay, I will send it to announcement. You're welcome. Okay, so let me see, where am I? I'm here. I can probably skip that. This is just saying that the NFS is utilizing all this this part of the kernel using network protocol and device driver in order to do that. I mean, I'm going to skip this. Okay, so now I'm actually going to lead into the issue about stateful versus stateless, and which stateless we already discussed. Essentially, the server is really lightweight, and we rely on the client to remember a lot of things. But on the other hand, the stateful, essentially we want the server to do some kind of maintain some of the information about a session that correspond to a particular client. Okay, so that is the top part is a stateful. This part is a stateless, and I usually using this picture to represent the stateful versus stateless. The the top is actually stateful, and the bottom is actually stateless. So essentially, if you're doing, so let's actually talk about stateless first. In stateless, when you actually open the file, it's not going to bother the server because you open yourself. And if you want to do some file, access the file status, it's not going to access the server as well. But if you do lseek, which is you moving the head of the file, it's not going to bother the server. But when you do read, then you have to read with offset. That's actually basically the stateless. In contrast, the stateful actually looks this way. Stateful, essentially, when you open, you actually open the file. You have to go to the server, but in a lot of this design about stateful file system, at the time when you open the file, if the file is not too big, you essentially grab the whole pieces, or at least a chunk of the file that you want to read to the client side. So essentially, when you open it, you actually bring a lot of data, the content already to the client side. And therefore, when you're actually doing read, you actually don't go over there to read the file because you read your local copy. So essentially, this blue circle represents your local copy. And when you want to do some kind of state update, you update your local copy as well. And of course, when you close, that means you actually save it back. And also you can do lseek, so such that you want to move the header, and then so you can actually obtain the next block of data. So this is a contrast with a stateless. So you can see that the design of a stateful, by the way, I should pull back a little bit. The earlier generation of NFS suffer a lot for access from a large number of users. And typically, when your number of users try to access the file system go up to a certain place, then the NFS server, their response time will get dropped down quite a bit. And one of the things that this actually saves that is that you actually, because every single read, every time you actually read a position or write a position, you're going to submit the request to the server. So the server, both the CPU capacity as well as the network capacity will be challenged because you have lots of read from all the client coming in, try to get this data. But think about stateful. We believe that people coming to this file system at different time, even though they stay on to do the work. And when they actually open it, they actually got the file one time. And then after that, you're basically just doing local. Because you're doing local, then you're not bothering the server. So the server is the load get distributed to all the clients. So that's the major advantage, that because of that application scenario, people think that stateful is a better approach for doing that. Okay, so I'm actually going to stop here because the next topic I'm going to talk about is AFS, the Andrew file system. Any question for today's lecture? Okay, so just to let you know, I will, by default, will go to in person next Tuesday. But if you cannot do it, let us know. If for some reason, for example, I got tested positive, then I will immediately send everybody a message. We're going to do everything online. Okay. All right. You all have a good weekend. Bye-bye.